Next we have Tom Crowe. Tom Crowe is the team lead for HPFS at IU. Mark Stearman's not here, so I mean I don't have any immediate sort of fun facts in the bios, but Tom I think knows that I miss Mark, so he included the fact that he's a fireman and an EMT. So ladies and gentlemen, Tom Crowe.
Good morning. Welcome again to Indiana University. My name is Tom Crowe, and I'll be sharing with you today some of our experiences with OST data migrations using ZFS snapshots and ZFS send and receive. I've included the full text of the abstract just for documentation purposes. That way, if you go back and review this later and you're interested, it's all there, but I'm not going to read it to you. The highlights from the abstract is basically ZFS, the snapshot send receive method is another tool in your data migration toolbox, and it may not be right for every circumstance. You want the right tool for the right job. In our experiences, this method can reduce your final sync downtime, which we'll go into some examples later. In this process of snapshot send and receive, the underlying ZFS structures can change, but the Lustre information is exactly the same. So you could have a different ZFS, what we would consider kind of like an inode or a ZFS object ID, but it will still have the correct Lustre object ID. This is a very good method for migrating from an older set of hardware to newer hardware where both are under ZFS's control. So you can have an existing source pool from old hardware and a destination Z pool with new hardware. And if you ever needed to change the geometry, so you have an OST that's running in a pool that is underperforming or that you need to migrate that to a different pool, that could also be a good fit. Some of our reasoning for pursuing this is that we've undergone a couple file system migrations using file-based tools, and we've tried to spread the load out and do as much as we could to parallelize efforts, but there's still a lot of time spent analyzing and comparing billions of files. And what we've realized after a couple of migrations is that our final sync takes a long time, and there's a lot of time spent in the comparison and not a lot of time spent in actually transmitting any deltas, any changes. And so we were looking for a way to cut down on that. As Ken had mentioned, we have a ZFS file system in production today, so we wanted to try to leverage any tools that we could using ZFS. So we'll go through our method here. Just a quick overview of our production environment. It's relatively small file system with 2 MDS, 4 SS. It gives the feeds and speeds there of the operating system. We are using Lustre 2.8 and ZFS 6.5.2. And it's worth noting that everything is hardware RAID, even though we're using ZFS to manage that. So one of our goals is that when we migrate to fully JBOD, fully ZFS protected back-end storage, we can use this method to get there. And so for our demonstration purposes, we replicated our production environment and kind of sized it down. So we have a single MDS, 2 OSS nodes. We use XCAT to provision our systems. So this is our demo environment is a logical mirror of our production environment, even though they are running on KVM guests, and obviously the hardware is different. The systems are built exactly the same as production, same versions of everything. So here we'll go through the basic OST migration steps as an overview. So within the pool, you have a target OST, and you would take a snapshot of that source OST. In the example here, it's OST1. And so after you take that snapshot, the next step is to transport that. Once you've taken a snapshot, it frees up the data in a way that you can copy it without anything changing underneath. So you use the ZFS send and ZFS receive mechanism to transport that data to your destination Z pool. And then you basically repeat that snapshot send receive procedure as many times as you need to. So the subsequent, the initial snap send receive is like a full copy. So it's going to, if your OST is, 20 terabytes in size, it's going to transmit 20 terabytes worth of data. And then your subsequent snapshot send receive is an incremental operation. So if there's only been a couple of gigabytes that have changed, that's all that's going to be transmitted in the secondary snap. And then as you go along, you want to clean up your original snapshots. Snapshots do consume space and your Z pools, so you kind of have this rolling snap, send, receive, delete type of operation. And what you'll find is that you can get down to a comfortable timing effort. So if you're snapping every hour or every 12 hours or whatever interval works for your site, you're gonna kind of get an average of, we see so much change over this period, and it takes us, on average, so many minutes or so many hours to transport those changes to the destination. It's going to give you a very comfortable and confident number for that final sync downtime. So when you're ready for that final sync, when you've done enough iterations that you're comfortable, you would stop Lustre, you would unmount your OST in question so that there are no changes occurring. It's completely unavailable. You would perform your final snapshot send receive operation, which again should be an incremental. It's your last incremental. You would edit your startup configuration files. So in this example, it's the ldev.conf. So you're going to change whatever your source mount is. So you would change from zpool-1 OST1 to zpool-2 OST1 _rep. You would change that so that when it mounts it, you're going to mount this destination or this replicated OST. And then when you start up Lustre, it's going to have the same logical mount point, just pointing to the different back-end block device or ZFS device. So this is really kind of a walkthrough of that overview. I don't want to dwell terribly much on each slide. It's intended that if you review this at a later time, you can try this out and hopefully use it, see if it works for some of your migration efforts. So what we started with was a brand new file system on our demo environment. We created 2 OSTs, and they're referred to there as demo 17-0000 and 0001. You can see their size. There's really nothing there. And our intent here is we're going to replicate, we're going to be working on OST 0000. This is just to illustrate that there was no data there. There's virtually no inode usage. This is how it looks right after you run the MakeFS. We did, in our demo environment, in order to keep the capacity usage down, we changed one of the properties in the ZFS dataset, which is the record size. It defaults to 128K. We changed that to 1K, so basically we could create about 1 million files and not need as much capacity on disk to accomplish that. It's also, you know, our user environment is one that they love lots of little files. So that's kind of what we wanted to replicate here, is just a bunch of small files. And so after everything was set up, we went ahead and populated the first OST there that we've referenced with about 1 million files. You can see the relative capacity and inode counts there. So we've kind of set the stage for this experiment, or this replication. And this is just from a ZFS perspective, what you could expect to see from the various commands and their output. One thing that, you know, kind of the initial step that you need to ensure is that your destination Z pool has capacity to receive whatever your source OST is. So in this example, on top, the highlighted OST is roughly 1.75 gig in use, and the pool that we're going to be migrating to is on the bottom there, highlighted OSS pool 02, and it has, you know, just under 6 gig free. So the point here is that you have to have free space wherever you want to replicate to. You do not want to discover that you do not have enough free space mid-transport. So first step here is you take a snapshot, and the commands are outlined there at the top. Or, pardon me. First thing you should always do is check for existing snapshots. As you get into this more, it's going to be very important to understand what snaps are currently on the system, if you need to clean anything up. So, and that top listing there, you can see there are no snapshots available, or no data sets available. And so then we create our initial snapshot with that ZFS snap command. If you notice to the right of the ampersand, everything to the right is what is called the snap name. And we've tried to use a meaningful snap name, one that allows us to easily identify when was this created, because the snap name, it'll let you use anything you want. You could say OST at just before lunch, or OST at, you know, pre-upgrade, or whatever. So we use the year, month, day, hour, minute, second output to help us keep track of when things happened. And so then you do your full copy, or your full replication, and the command is highlighted there, and I'm not going to go through it too much. The capital R is for indicating a replication stream, and then you pipe that into a ZFS receive and point it at the target pool or the receiving pool, and whatever OST name you want, or whatever VDEV name you want it to be. So we typically use the same OST name with an underscore replicated, but again, you could rename the OST at that point if you, pardon me, you could rename the VDEV at that point if you wanted to. And then the verbose output will give you 1 second intervals to let you know data is being, you know, actively transported, and when it quits those outputs, you know, the replication is complete. This can give you some, as I mentioned, some timings or some, you know, intervals that you can compare as you get into the incremental sends. So after you've created that snapshot, if you run your snapshot list command again, you'll see, after we've created it and replicated it, you'll see we have a source snapshot and a destination snapshot. And when we run our ZFS list command, you can see both the source and destination VDEVs or OSTs. If anyone picked up on the size differences between the two, that's a result of changing the record size at the beginning. You'll notice one says 1.76 gig in use and one says 1.48 gig in use. So when we change the record size from 128K to 1K, you can account for that missing 318 meg of space because of that. So after our initial snapshot send receive operation, we're doing the subsequent incremental snapshot send receives. The snapshot command is exactly the same. You're giving it, you know, a meaningful snap name. Then you can see the output of, you know, the ZFS list. And when we transport the incremental snapshots, you use the -I switch in the command. And you also have to provide kind of a start and end snapshot to say, I'm interested in the changes between here and here. And then the pipe into ZFS receive is exactly the same, and you send it to the same VDEV name that you chose before. We didn't make any changes on this example, so it was an instantaneous, you know, send. And then cleaning up your old snapshots is important, as I mentioned. If there were active changes, those snapshots are holding those copy on write changes, and you'll want to clean that up as you go so that you don't run out of space on either the source or destination Z pools. The ZFS destroy command, which is how we're cleaning up the snapshots, as it's noted there, it's not going to ask you, are you sure, or did you type it right? It's just going to delete it. So please make sure that you have the syntax correct before you issue that. And then you can follow up with your ZFS list command to see, did it delete the snapshot that I expected it to. Once you've gone through all these incremental snap, send, receive, deletes, and you've kind of got your timing down as far as it takes X number of minutes or X number of hours to, on average, get this OST from the source to the destination, you can plan for your final synchronization. And so here again, you would stop Lustre, you would stop that OST so that there were no updates occurring to it. You would edit your ldev.conf or whatever your startup mechanism is for changing the mount options or the source device of the mount. You would perform your final snap, send, receive operation. And this is just, you know, receiving that final snapshot. And you can see in this example, there was some data that had changed. It took about 3 minutes for that final synchronization. And then we went ahead and started up that OST specifically. And, you know, as far as Lustre knows, it's exactly the same as it was when you shut it down, because nothing has changed, because nothing has been accessing it. That final snap, send, receive operation brings it in line with the source. So they're mirror images as far as the data content. This is just a, you know, high-level overview of those steps again and the various commands. I don't need to walk through those. Again, it's intended for follow-up if anyone wants to step through this. Everything should be inclusive. And it's very important, I guess, to note that the ZFS destroy operation is, it does impact the entire pool. So even though you might think that that should only impact that snapshot, it will put cycles on the entire pool. So it's typically very quick, but if you have a very, very large snapshot, it may take a bit longer than you expect. Again, to summarize, the rhythm is a snapshot, send, receive, destroy, and you keep performing that until your final sync. For the final sync, you would stop Lustre and or the OST in question, perform that same snapshot, send, receive, change the startup config of that OST, and then bring that OST online. There are performance and capacity impacts, as mentioned. You know, it's not a silver bullet or magic or anything. You can monitor those impacts with the zpool status command, or zpool iostat will give you both the capacity outputs or the IOs as ZFS perceives that. This method is extremely efficient in transporting of incremental changes because it's truly keeping track of just what has changed, as opposed to a file-based method that has to first take a look and say, is the source the same as the destination? What has changed? I can transport that. This method, as mentioned, is appropriate for predicting or controlling your downtime. If you have back-end storage changes that are both under ZFS's control, it is a very eloquent way to migrate over, and if you wanted to do any zpool geometry changes. So we did a quick comparison with our demo system of the same source data. So, and the examples from before, we were working on OST 0000. We generated about 1 million files. It had minimal capacity in flight. And so when we did our initial snapshot send receive operation, in this example, it took about 33 minutes. So from 10:29 to 11:03 there. We used the exact same source and destination pool, so the same hardware, and we ran an rsync command to kind of compare. Now this wasn't parallelized, it was just one rsync command. We didn't have a bunch of threads or, you know, different clients. And as expected, you know, it took rsync a while to compare things and transport that. So our initial findings were that the snap send receive was about 3 times quicker than the rsync method. And this is in no way a slam to rsync, because we use it a lot and it's a great tool, and if the right migration calls for it, it will fit far better than the ZFS method I'm talking about. In our use case, we tried to use as many clients as possible and spread out the lists, and it was still a very long final synchronization time. And so what we did is we then took that OST 0000 and we modified about 150,000 files of the 1 million files, and we just appended 8 bytes to the file. So it was a very small data update, and about 15% of all the files there. And so when we did the incremental snap send receive, it was fairly quick, only 2 minutes, because the snapshot is keeping track of those changes specifically, as opposed to having to reevaluate all 1 million files to say what has changed. So 2 minutes for the incremental snap send receive. Rerunning the same rsync command, again, single client, single process. It was roughly 101 minutes for that same operation. So there was a lot of overhead, or there is a lot of overhead in comparing long lists, and there's also the underlying metadata calls to say, you know, how big are you, what's your timestamp for both the source and destination. There's no metadata calls in doing the ZFS snap send receive method. So that's, you know, just for graphing purposes, it's 50 times longer in that example. Some of the things that we've learned from trialing this is that, you know, rsync, like I mentioned, it's a great tool, and we've used it before, but there is overhead, no matter how much you can spread it out or you know, parallelize its lists, there's an overhead to check the source and destination. When you're talking about millions or billions of files in our examples, it takes a while just to compare the lists. The ZFS snapshot send receive method, you know, it operates underneath Lustre, so there's no metadata, no Lustre metadata calls that are needed to compare anything. If your environment has an extremely high rate of change data, this would not be a good method. You know, it's very likely that the snapshots could grow larger than the original OST sizes. And again, the right tool for the right job is what you really want here to optimize or to, you know, minimize your downtimes when doing data migrations. This is another tool, hopefully, if you're using ZFS, that you might want to investigate. But as mentioned, it may not be the right tool for the job that you're trying to accomplish. Some of the things that we plan to do in the future, as mentioned today, one of IU's production file systems is ZFS based, and we're using hardware based protection, and those block devices are concatenated into our Z pool. So ZFS is controlling, or is in the middle there, and once we decide to migrate off of this hardware based storage onto fully JBOD ZFS protected storage, we should be able to use this method, and we should have little to no downtime in accomplishing this. It's also one of our intents to use this method in order to migrate OSTs either in or out of pools that are experiencing collateral damage from other OSTs. So you may have a hot OST, someone who's, you know, writing or reading a lot to it, and that's causing the Z pool as a whole to be busy. So you could migrate that hot OST into a more free pool, you know, less used pool from a performance perspective. And another thing that we might, or that we'd like to pursue is making full offline copies for other research efforts like the Lustre project that Ken mentioned. Sometimes they want to, with that effort, they want to really take a deep dive on the data, and it's a little unnerving to think about doing that on production data. So getting a full copy that you can store anywhere else and do whatever you need to is very attractive. So these are some of our references. You know, there's examples and good documentation on both of these URLs, and then the 4 individuals mentioned below, we've had the privilege to ask them many, many questions, and they've helped us along the way to get the answers we were looking for. So if anyone has any questions, I'll be glad to try to answer those.
Yeah, this is about, just wanted to know if you have tried a few use cases. The first one is if you've tried migration of OSTs across different servers. So OST on, let's say, server 1 and to another OST on server 2.
We have not tried that. It is very possible. So I did not include in any of the examples that ZFS send can be piped into a transport mechanism like SCP. So you could transport your snapshots between systems. It would be very important that the destination system was properly, let me back up. it would be important that the service node flags were designated on the OST so that the destination system's NID matched what the OST was willing to run on. So yes, we have not tried it. It will work. I'm confident that it will work, but you need to have the failover set up correctly on the OST so that wherever you're sending it to is designated as a service node as a part of the file system flags.
Okay, thank you. And another use case I was talking about was the partial OST migration. That means, let's say, you mentioned about hotspots. Let's say you have two files, A and B, and which are hosted on OST 1, causing, let's say, performance problems because they are hosted together. And you want to migrate only file A or the blocks, objects belonging to file A. So have you tried or have you thought about partial data migration between OSTs?
So if it was a file-specific issue, I think the LFS migrate tool would be better to move that, or you could use rsync to do that during a maintenance period. The OST as a whole, so if you were looking at the zpool iostat output, you might see that this one OST is constantly doing so much more IO than any other OST. And you may determine that you want to isolate that OST in a different pool. So that would be the scenario where migrating a hot OST might benefit. But if it were a single file or a group of files, I think the LFS migrate tool would be a better approach to spreading that out or to moving that to a lesser used OST.
Okay, thank you.
Yep. Thank you.